Hello, so let's talk about CIDR a little bit. Just make sure it's you have a decent understanding of what CIDR, because it'll help you with the understanding of the VPCs and the subnetting and everything that we're going to be learning. So I want to start with this video. This is a video from Harvard University's CS50 class. This one specifically is for lawyers. I really like it. I really like these courses that they have. They're for free at no charge. And I want to go ahead and play this one because I like the way they explain IP addresses. So let me get to the exact spot that I want to be in. Let's see. Hit play and give it a second. So we want to talk about IPs.
Hashes can be any value between 0 and 255, and that range 0 to 255. Well, that's 256 total possible values. That's 8 bits. Ergo, each of these placeholders represents 8 bits, 8 more bits, 8 more, 8 more. So an IP address, by definition, is 32 bits. And there it is, IP, an acronym you've probably seen somewhere.
Okay, just as to talk about, he's talking about 32 bits. So there's 4 things there. There are 8 bits each. 8 bits equals 1 byte. So just kind of remember that terminology. 8 bits equals 1 byte.
Or even if you've not thought hard about what it is, it stands for Internet Protocol. Internet Protocol mandates that every computer on the internet, at the risk of oversimplification, has a unique address called an IP address. And those IP addresses look like this. If these IP addresses are composed of 32 bits, how many possible IPs are there? And therefore, how many possible machines can we have on our internet? Well, 2 times 2 times 2, 2 to the 32. So that's 4 billion, give or take. By design of IP addresses, you can have 4 billion, give or take, possible permutations of zeros and ones. You have 32 in total, and that gives you 4 billion maximally computers and phones and Internet of Things devices and the like. Now that sounds big, but not when each of us personally probably carries one IP address in our pocket, in our phone, maybe another on our wrist these days, 1 or more computers in our life, not to mention all of the other devices and servers in the world that need these addresses too. So long story short, this is version 4 of IP. It's decades old, but there's also a newcomer on the field called IPv6, version 6. There isn't really to be a version 5, and IPv6 is only finally gaining traction because we're running so short on IPs that it's becoming a problem for campuses, for companies, and beyond. But IPv6 will use 128 bits instead of 32, which gives us many, 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 many more possibilities, bigger numbers than I can even pronounce. So that should cut it for quite some time. But not every computer on the internet needs a public IP address, only those envelopes, so to speak, that need to leave my pocket or my home or my campus or my company. It turns out as a short-term mechanism to squeeze a bit more utility out of our 32-bit addresses, which are still omnipresent and the most popular among the versions, well, we can actually distinguish between public IP addresses that do actually go out on the internet and private addresses. And indeed, if your own IP address happens to start with the number 10 and then a dot, or the number 172.16 and then a dot, or the number 162.168 and then a dot and then something else, well, odds are your computer has a private IP address, and this is just a feature.
Okay, so what I want you to do is go into, I have an iPhone. I don't know, I'm assuming it would probably be similar if you have an Android. Go to settings, and then you would go to Wi-Fi. If you're not connected to the Wi-Fi, you need to be connected to the Wi-Fi. And once you're connected to the Wi-Fi, wherever you're at, you open up that Wi-Fi connection, and then you scroll down a little bit, you'll see an IP. Again, I'm on an iPhone. You'll see an IP4 address, and then it says the IP address, and like he says earlier, it begins with a 10. So that indicates it's a private IP address. I'm on the Hocking College network, so I'm assuming that's following suit on that. And the way you can check on, I'm not going to do it on the screen. I'm not going to necessarily share it, but I will to a certain point. I'm on a Windows computer. So if you are on a Windows computer, let's see, all you got to do is type in command, open up the command prompt. My computer's like really slow. Give it a minute. Okay. And then I think it's just IP config. I'm not going to hit enter because then it'll show my IP address, and that could be a potential security flaw, or if somebody wants to hack into it. So I'm not going to do that, but you just type in IP config and hit enter, and then it should show you your IP address. So those are two ways that you can find your IP address, for a phone, and then on the computer. Again, that's for Windows and iPhone. I'm assuming it'd be fairly simpler, fairly similar to Android and Linux-based and Apple-based operating systems. But that's how you can find your particular IP address. Let's see. But I did test it earlier, like the one I said on my phone, it begins with a 10 because I'm on the Hocking College Wi-Fi, and the one that I'm actually connected, because I'm connected to the Hocking College network on this computer right here, and it begins with a 10 as well. So let's go ahead and continue to play.
Of the little router that's probably in your home, or the bigger router on your campus or corporate network that enables you to have an IP address that's only used within the company, only used within your home, and cannot, by definition, be routed publicly beyond your company, beyond your home, because the router will stop it. And so here we actually have the beginnings of a firewalling mechanism, if you will. In the real world, a firewall is a device that prevents fire from going from one store to another, for instance. In the virtual world, a firewall is a piece of software that prevents zeros and ones from going from one place to another. And in this case, do we already have a mechanism via public and private addresses of keeping some data securely, or with high probability securely, within?
So they talk about it within AWS. I'm talking about VPCs. There's a private subnet and a public subnet. So that's kind of what he's talking about on that. The private is within your university or your business, as you mentioned, and a public would be available to the worldwide.
In our company versus allowing it to go out on the internet. So we'll see now some screenshots of some actual computers, Mac OS and Windows alike, that reveal their IP addresses, and you yourself can see this on your own machines. For instance, here on Windows 10 is a screenshot of what your network preferences, so to speak, might look like. And if you focus down here, it's a bit arcane at first glance, but IPv4 address is 192.168.1.139 when we took that screenshot. And indeed, it starts with 192.168, which means it's private. And indeed, I took this screenshot while we were within a home network. And so that suggests it can be used to route among computers in that home, but not beyond. You'll see, too, if we move on to the next screen where you see more advanced network properties, you can also see the mention of this, default gateway, which is synonymous with router, default router, 192.168.1.1. So a default router or default gateway is that first hop, so that if I want to send an email outside of my home, I want to visit a web page outside of my company, all I need to do is hand that virtual envelope containing that email or that web request off to the machine on the local network that has that IP address. I have no idea where it's going to go thereafter to hops 2 and 3 and beyond, but that's why we have this whole internet and even more routers out there. The routers intercommunicate and relay that data hop to hop to hop until it finally reaches its destination. Now, where did I get my IPv4 address from? Where did I get my default gateway from? From the DHCP server in my home, in my company, or whatever network I happen to be on. And Mac OS is the same. If these screens are unfamiliar, you might recognize this in your system preferences in Mac OS. Here, while connected to Harvard University's network, you can actually see that the IP address was 10.254.16.242, that number 2 starting with one of those internal or private prefixes, indicative of the fact that even within Harvard, were we keeping all of our Harvard traffic internal to Harvard and then not exposing that externally? And indeed, if we look in the more advanced preferences here, we can see that the router for my Mac was 10.254.16.1, which is to say this Mac, when it's ready to send something off campus, simply hands that envelope off to this particular router here. And the router's job, ultimately, that first hop, a border gateway or a border router, literally referring to a computer that physically or metaphorically is on the edge of a campus or company, its purpose in life is to simply change what's on that envelope initially from the private IP address to one or more public IP addresses, thereby maintaining this mapping. So this might result in everyone else in the world thinking that I and you and everyone else in my company or campus are all actually at the same IP address, but that's not true. each of our personal devices has a private IP address, and that router can actually translate via something called network address translation, or NAT, from a private address to public and back. And so in this way, too, can a company help mask the origin or the identity of whoever it is that's accessing some internet-based service. Of course, that same company could log what it is that's leaving the company and coming back in. So by a subpoena or another mechanism, could someone certainly figure out who was accessing that service at a particular time? But the outside world would need help knowing that. And so here, even within Harvard, it's done perhaps for that reason, but also perhaps in order to use one public IP address among hundreds or thousands of university affiliates, so that frankly, we just don't need as many IP addresses. So what might be both a technological motivation can also have these policy side effects as well.
Okay, so that was I think it was a good way to explain IP addresses and some of the differences in the terminologies that you're hearing with AWS. So let me get back to my presentation. And hopefully that helped kind of clarify. And I will be the first to admit I am not good with numbers. Numbers, yeah, they're not my thing. So there's like whenever we talk about bytes and bits, I mean, there's 8 bits, meaning 8 binary, meaning 0 or 1, on or off. And that's a bit. And there's 8 bits into 1 byte. Okay. So 8 bits equals 1 byte. Now, whenever we start talking about IP addresses, there's like a lot of numbers and it's like too much for me. So just bear with me on that. It's not my forte. It is what it is. And I don't really try to understand the computation behind it. So what is an IP? So it's an internet protocol. Some of the stuff David Malign, who you just saw with Harvard, he was explaining that. So it's an internet protocol. It's a protocol for communication on the internet. And so the breakdown of an IP address is broken into 4 octets, which are bytes. So octets and bytes are synonymous. And the bytes range from 0 to 255. And what that means, so for every bit, and a bit can be 0 or 1. It can be on or off. When I say on or off, like off is 0 and on is 1. And so between the 8 different characters of zeros and ones, within all the ways that you can mix that up, equals a byte anywhere from 0 to 255. And I might make another video kind of doing a breakdown. Don't want to go too deep in the rabbit hole, but I'm not sure what everybody's understanding is for bytes and bits and whatnot. So I might make another video explaining that and be using Harvard University's stuff as a resource. But anyways, so basically there's 4 bytes, which makes up 32 bits, because 4 times 8 equals 32. I know that. Okay, what is your IP? So we talked about that earlier. I'm going to pause the video. Those are the ways that you can find your IP address. So what is a CIDR? A CIDR is a method of assigning an IP addresses to improve efficiency and address distribution. So as he was saying in that video earlier, the number of IP addresses that we're kind of running out, 4 billion sounds like a lot, but when you think about, like, on my desk right now, I have this computer that I'm talking into, I have my Apple Watch, and I have my cell phone, and that's all. I have a laptop in my bag down there, and I think that's all I got. But and I have Alexa in my office. So those are all things that take up IP addresses. So in my office alone, I have 4. 1, 2, 3, 4, 5. So when you take into consideration how many devices we have, it's 4 billion, it's going to run out. So they came out with IPv6. I kind of digress a little bit. Okay, but anyways, a CIDR is a classless interdomain routing. I always forget what it stands for. I had it up in here at the beginning. Classless interdomain routing, yes. Okay. As a method of assigning IP addresses to improve efficiency and address distribution. So basically, when an organization has an IP address, it may not need all the IP addresses that it could be associated with it, all the numbers, basically. So it's just a way to improve efficiency. So who uses CIDR? So network engineers use CIDR, and a network engineer can also be a cloud engineer. Use CIDR to divide IP addresses based on the needs. So the CIDR is structured. It's made up of two sets of numbers. There's a prefix and a suffix. The prefix represents it's a binary representation of a network address. And we'll show an example here in just a second. And the suffix declares the total number of bits in the entire address. So a CIDR with a 16-bit subnet. So you can see I got some color coded there to kind of help with this, but 10.10.0.0 and 16 suffix. I don't know the exact correct way of saying that. It's 10.10.0.0, 16 suffix. There's probably no correct verbiage. Will allow the creation of up to 65,536 IP addresses. Each address will start with a 10.10, and the 00 can change to any value between 0 and 255. So just anything between 0 and 255. Those two zeros, the ends purple, can change anything between 0 and 255. So once you do the math on that, this will create 65,536 variations of an IP address. I'm just taking that for face value of saying they said 65,000 and 65,000. I'm not going to try to do the computation of that. That's too much math for me. Okay, and the 16 indicates that the first two octets, which remember, and each of these bytes, this 10 is a byte, this 10 is a byte, the 0 is a byte, the 0 is a byte. Each byte is made up of 8 bits. So the 16 represents the two octets, which are these first two bytes. So 8 times 2 equals 16 would be the same. So all this would start with the 16-bit subnet. The 1010 is the same. The 00s can change anything between 0 and 255. That equals 65,536 variations of this IP address. Okay, so, and then another example would be this. So with a 24 CIDR block with a 24-bit subnet. So it's 10, 10, 10, 0, 24. So this will allow only for the creation of 256 IP addresses. So that's because these first three 10s are all going to be the same. Like these first three 10s were indicating that this will not change. The only thing that can change is a 0. Now 0 is a value in itself. So even though it can go up to 255, you add that 0 because 0 is a value when it comes to binary. And so that's 256. So this will create 256 variations of an IP address. Now, having said that, some of those numbers are reserved. I don't remember which ones, but there are some reservations on, and I think that VPC video kind of addressed that a little bit. There are some numbers that are reserved that you cannot use. I don't remember what those are off the top of my head, though, but just kind of focus on this right here. So this is going to represent 256 variations of this IP address. And again, the 24 indicates that that should be first 3 octets would be the same. So I need to change that. But this should be 3 instead of 2, like right here. So this one right here, because 8 times 3 equals 24. I think that was okay. So these are some of the resources that I've used. If you wanted to take a deep dive, when you're studying for this AWS exam, you don't need to have like a really good depth of understanding of some of this terminology, but it helps to have like a basic, it's like you're not completely foreign to you. It's like, because sometimes with these exam quizzes or these exam questions, there needs to have some understanding of a CIDR. It's like you don't want to be completely blank on what a CIDR is. You want to have some basic understanding, foundational knowledge of what a CIDR is. It doesn't mean you need to know the math and all that in depth, because that's just like, not at this stage anyways. But you need to have like a basic understanding of it not being completely foreign to you. So these are some other resources that you could use, that I use when pulling this together here. That might help. So hopefully this kind of helped. If you have any questions, let me know. Thank you.